This is my presentation for lab number 1 of Physics 2211. My name is Dominic Finelli and this lab is on constant velocity motion. Introduction. So the goal of this lab is to compare the observed position of an object moving at a constant velocity to the predicted movement of that same object based on a coded model. This lab makes use of Newton's second law, comparing the movement of a pen with the tracker to the model produced by my constructed code. Newton's second law plays an imperative role in this lab as it provides an explanation for constant velocity itself. In order for constant velocity to actually exist, the forces that are acting on the object have to cancel each other out. Net force has to be zero, which is explained by Newton's second law. So here's the video of the pen actually moving. So as you can see, as the pen moves, the data points are tracking its position and data is being compiled right here. And that data can then be put into an Excel spreadsheet and then turned into a graph, which you can see right here in this dot plot, position versus time. So now we have to create the code to actually create a model of this. And with the starter code, we're missing two values. We're missing time and we're missing initial velocity. So finding time is fairly simple. It's just the time that the pen is moving. So that's the last value of the time in the spreadsheet, so 0.266667. However, finding initial velocity is a little bit more complicated. But since we know that net force is 0, when we manipulate the Fnet equation, Fnet equals the change in momentum over change in time, we can manipulate that all the way down to this, to final velocity equals Fnet times delta t divided by m plus initial velocity. And since Fnet is 0, when we plug in 0 for this entire section cancels out and we're left with final velocity is equal to initial velocity. And since we know that final velocity is equal to initial velocity, then they must also both be equal to average velocity due to the average velocity formula. So average velocity is pretty easy for us to find, so we can do that using average velocity equals the change in distance over the change in time. We already have the change in time at 0.267, and then we can get the change in distance easily by going back to the Excel spreadsheet. It's just the time, or the distance that the pen traveled, 0.531. So when we put that into the formula, we're left with V average equals 1.988 meters per second. So now we have those two values. We have 1.988 up here, and we have 0.267 right here. We're able to run the code, and we're left with this. So as you can see, we're given values at the bottom to be plotted, and we can put those into the Excel spreadsheet as well. So here we have the initial data we have, here we have the new data, and when we plot it, you can see that they're pretty close. However, the observed position is a little bit off, which leads us to believe that there could be some issues with the tracker. So what if the axes were flipped in the tracker? If the axes were flipped, it would simply be like reflecting this graph across the x or the y-axis. If the x values were flipped, we could just reflect it off the y-axis and it would make the position values negative. And if we flipped it across the x-axis, it would make the time values negative. So either flipping of the tracker is just making certain values negative. What does it even mean? Is it possible for you to say how many pushes and pulls are acting on the object when net force is equal to 0? No, it is not. Since there's no change in velocity, then all of the forces are canceling out, and there could be an infinite amount of forces acting on the object. All that we know is that they're all canceling each other out, and that net force is equal to 0. Thank you so much for your time. That is all, and have a good one.